welcome back to Study Journey. It's Mary and I'm back with another AMC Problem of the Week 10A problem. And this is going to be about equilateral hexagons and how to use relationships to make an equation and then solve the problem. So without further ado, let's get on with the video. This is AMC 10A Problem 19 from the year 2010. Equiangular hexagon ABCDEF has side lengths AB equals CD equals EF equals 1, and then BC equals DE equals FA equals R. So we know that it is an equiangular hexagon, and then we know these side lengths equals 1, and then these side lengths equals R. The area of triangle ACE is 70% of the area of the hexagon. 70% of the hexagon. Okay, and then it is asking you what is the sum of all the possible values of R. So sum of all possible values of R. So I quickly sketch out this diagram here, and then it's definitely not drawn to scale, but we can mark out what we already know. So we know AB equals CD equals EF equals 1, so I just drew a little tick mark. And then these three lines are equal, they equal R. So this is 1 and this is R. So since we know that this is also an equiangular hexagon, that means all of these interior angles are equal. So since we know these two sides are the same and then the middle angle is the same, which is side angle side, which is SAS, and then that is how we prove two triangles to be congruent. So we know that these two triangles, or these three triangles altogether, are congruent to each other. They tell us that the area of triangle ACE, which is this middle triangle, is 70% of the area of the hexagon. So we have to try to figure out what is the area of the triangle and the hexagon so that we can put it together into an equation. Since we know the side length of AB and BC, which is 1 and R, we are trying to find basically the side length of one of these, because we know that all three of these are equal because these three are congruent triangles. So we just have to find the side length of one of these triangles. So using the law of cosine, so we're going to use the law of cosine, which states that in any triangle ABC where the side lengths are relatively A, B, and C, and then there is an angle that we know, which is alpha, then we can know that the third side, which is the side C that we don't know, is equal to the square root of A squared plus B squared minus 2AB times cosine alpha. So let's apply this into our triangle ABC over here. We know these two side lengths, so we're going to say that AC is equal to this C. So AC squared, if we square this whole thing over, this would equal A squared, which is 1 squared, and then R squared minus 2 times 1 times R times cosine alpha. So here in this triangle, this ABC, the alpha would equal this, and then we know that equiangular hexagon, the interior angles are 120 degrees, so this would be cosine 120 degrees. But we know that when we use the law of cosine, we usually use radians instead of degrees. So how do you go from degrees to radians? The formula is the degree number times pi over 180. So here the degree number is 120. So if we plug it in, we get 120 pi over 180, and then that will be 2 pi over 3. So now let's just simplify this. So as you can see, cosine of 2 pi divided by 3 equals negative 1/2, and then we can simplify that. So AC squared is equal to R squared plus R plus 1. Now that we know what AC is, we know side length of one of these side length of the equilateral triangle. So since all three interior angles are 60 degrees, we can also find the altitude. So now that we know that this is the area of triangle ABC, then we have to try to find the equiangular hexagon's area. So how can we do that? Well, let's try to make some lines. So let's extend BC and ED so that they meet at a point. Let's just call this point X, and then let's extend these two, AF and DE, so that they meet at a point. Let's call this Y, and then same for here. Oh, what do we see? Well, let me see. this is obviously a triangle XYZ. So what is so special about this triangle? Well, we can probably guess that this is an equilateral triangle, but we can prove it too. So because all these interior angles are same, because it is an equiangular hexagon, so these exterior angles are also the same, because 180 minus the same angle is obviously the same angle. And then since we know that all of these three triangles, they have the same two base angles, and then the base is also the same, which is 1, then we know that these three triangles are congruent because angle, side, angle, ASA. Okay, and we also know that the interior angles, these are 180. So the outer angles, these are all 60 degrees. And then since this angle is equal to this angle is equal to 60 degrees, then this angle must be 60 degrees. So these small triangles right here, they are also equilateral triangles. Yay! So since the base is 1, we know that since it is an equilateral triangle, all of these three sides are 1. So CX is 1, DX is 1, all of these are 1. So a base here, like ZY, this would equal 2 plus R, because we know that's R. So now we know the base of the triangle. So from this equation right here, we can basically use that equation to solve out the area of triangle X, Y, and Z. Because it's the same concept. It is also a 60-degree angle, and so we know the height of this triangle and the base of this triangle's ratio is right here. So let's just use that to solve for the area. I'm just going to say that the height of this triangle is h. So h over the base, which would be zy, or 2 plus r, is equal to the square root of 3 divided by 2. And then we can just put this in. So we can see that the area of triangle XYZ is equal to the base, which is 2 plus r, times the height is right here, divided by 2. So let's simplify. Okay, now to find the area of the hexagon, we can just use the area of the triangle XYZ and then subtract these three congruent triangles from it. So we know that the base length of this equilateral triangle is 1, and then from here we can tell that if the base was 1, then the area of one of these small equilateral triangles, or the area of triangle CDX, is equal to the square root of 3 divided by 4. So all three of these together would be 3 times the square root of 3 divided by 4. So what is the area of A, B, C, D, E, F? This would equal the area of triangle XYZ, which is the square root of 3 divided by 4 times r plus 2 squared. And then you minus the 3 equilateral triangles, which is 3 times the square root of 3 divided by 4. Now, let's look at all the information that we have. We know the area of triangle ACE, which is this, and the area of triangle XYZ, which is here, and the area of one of these small triangles, and all three of them together is right here, and then the area of this hexagon. Whew, how can we put all these stuff together? Well, it tells you that the area of this triangle ACE, is 70% of the area of the hexagon. So this is 70% of that. So let's just write this out as an equation. The square root of 3 over 4 times r squared plus r plus 1, that is 70%, which is 7 over 10 times the hexagon, which is, by the way, I simplified that to this. Okay, so if we simplify it and solve all of this out, we can first cross out these two, and then this would equal r squared plus r plus 1 equals 7/10 r squared plus 7 times 4r divided by 10, and then plus 7/10. Simplify some more, and then we can finally simplify to r squared minus 6r plus 1 equals 0. And then let us find using the Vieta formula, let's find that the sum of the possible values, which we know is negative of the b value right here over the a value, which is 1. So the sums of the two is equal to negative b over a, and in this case it would be negative of negative 6 over 1, which equals 6. You can barely see that, but whew, we're done. Let's take a look at the answer. So our answer will be E6.